The percentage of the blood volume? Or the molecule of the blood volume? Did you tell me that osmotic pressure is a pulling force exerted by solutes on their solvent? Did you tell me that a hypertonic solution is one which pulls water more strongly than another does? A hypertonic solution is one that has a great amount of solutes in it. So that they're going to pull water towards them more strongly. Then another one that you're comparing it to, right? It's a comparative term. It's a relative term. Did you tell me that an enzyme is a protein that makes a chemical reaction more likely to occur or it occurs faster? Did you tell me that a solute is a substance in a solution that makes up the smaller percentage of the solution? You know, the solvent is the thing that's in higher concentration in the solution, right? If a solution is an even mixture of two or more substances, one substance is in more concentration in the solution than the other. The thing that's in most concentration is the solid bit, right? And then you got some few bits of salts or sugars or proteins down there. Those are the solutes. So the solutes are, I don't know, this stuff dissolved in a solvent to give you a solution. That would have been a good. You don't have to say it the way I'm saying it.
So far,
What's
I
a
got a 6.
polymer? I tried to use the word several times before our quiz today. A polymer is a long chain of repeating subunits. Like a protein is a polymer of amino acids, or a complex carbohydrate is a polymer of monosaccharides, for instance. Everybody good? Not really, but okay. Well, we're moving forward anyway. Okay,
6,
so
I think.
before we stop to take a quizzy and a breaky, we were talking about the development of the platelets, and the next thing that we have to talk about is the blood clotting process called hemostasis, and we will. But before we go there, I think maybe the best thing, and I just did it this morning for the first time in all my 70, 80, 90 times a teaching class, whatever it is, I think it's best if on this picture right here, I tell you that we're about to learn 3 chemicals that are associated with the platelets, 2 of which we'll name specifically, and 1 which we'll just use a generic term for. But the platelets produce the famous molecule. They don't produce, I shouldn't say this, they release. The platelets release the famous molecule serotonin. You may have heard of serotonin before because it's a neurotransmitter in the brain. Serotonin is an important chemical released in your digestive tract for digestion. The body has co-opted it for many purposes around the body, so it does a lot of things. And another thing that serotonin does is it causes vasoconstriction, the narrowing of your blood vessels, to reduce the blood flow down the blood vessel. Serotonin is released from platelets to help cause vasoconstriction. I'm saying this word. It's the constriction of your vasos, your blood vessels, right? To constrict is to narrow. Serotonin helps to cause vasoconstriction, narrowing of the blood vessels so that less blood flows down. And we need to do that when a blood vessel wall is broken and then blood's leaking out. We need to narrow that blood vessel so that there'll be less blood loss out of there. Sort of like for the same reason that you might, if you were fixing the bathroom faucet, you would turn the water off before you're going to fix it, right? Turn the water off under the sink or under the house or something like that, so that while you're working on it, you don't want to have water shooting all over. That's the same thing. If you have blood leaking out of a broken blood vessel, you want to reduce that blood loss through vasoconstriction. Now wait, you can never turn off blood flow, so there's no longer blood flow, because downstream tissues would suffocate and starve. But you can reduce the blood flow so that we're losing less out of a broken blood vessel. Well, serotonin comes up with this and helps us to do that. Then, the second chemical that I want you to know about, we will not use a name for, but we're just going to refer to these as chemicals that attract more platelets to an area of blood vessel damage. Our book has committed to a particular suspect molecule, but I think that there's too much contradictory research out there, and I got a feeling they're going to be rescinding that in the next couple of years. So I'm not going to say the name of it, although you may find it in the textbook. Let's just leave it at chemicals that attract more platelets to the area whenever we need more platelets. You might remember in A&P 1, the formation of a platelet plug was the example of a positive feedback mechanism way back in chapter 1, where the binding of one platelet releases chemicals that attract more platelets than more platelets bind, releasing even more chemicals and attracting even more platelets. And you get this big amplification or magnification, a big acceleration of the accumulation of platelets to stop up a hole in the blood vessel so you stop losing blood. And then the third chemical associated with the platelets is called platelet factor 3, but you'll see it always abbreviated as PF3. Just stands for platelet factor. And these 3 chemicals here, let's say, are about to come up in our story of how blood clotting happens, how we seal small tears in blood vessels. Well, I'm going to ask you to meet me at this picture in your handout packet. It means you have to go a little bit backwards. Can I erase that list that's up there? Anybody need to take a picture or something before I get rid of it? It's still there, it's still there, we can go back. There it is. Okay, going once, going twice. I want you to have this picture that says, at the bottom it says hemostasis, figure 10.5, hemostasis. Hemostasis, don't confuse it with hematopoiesis, there's blood cell production. Hemostasis is to make something static. Stasis is to stop, right? We have to get the blood to stop running out of a broken blood vessel. We have to stop it from running. This is the process of hemostasis. When I photocopied this, I just wanted you to really get the picture, and maybe also that caption at the bottom, but not the paragraphs on the side. It was just an easy photocopy of the whole thing. We're going to use this picture from the baby book instead of using figure 17.13 from our textbook, although I will use the pictures because these pictures are what you see on here, but you can't tell because of the black and white on here. So we won't use figure 17.13. This picture's saving us from figure 7.13. And look, it's saving us from this nasty figure 17.14 with all these Roman numerals and an intrinsic and an extrinsic pathway. No, we'll save all that for Bio 564. We'll cover blood clotting to that level at some point in graduate school.
Yeah.
God bless you. And it'll save us from table 17.3, where all of these numerous known clotting factors referred to with Roman numerals and all of their specific roles, we won't need all of that. Because to cover this at our level, this picture will be adequate. But I'm trying to sell you on this picture right now by telling you what it's going to save us from in our textbook. Because this picture in itself is daunting. And when we get about halfway through, students are like, oh God, the hell with this. Where's the withdrawal form? So believe me, this is the lesser of the evils, this picture is. Start up here at the top left. See there's a circle? That circle is supposed to look like this picture at the top of our screen up here. It's supposed to be a picture of a broken blood vessel with a gap in its wall. And blood would be leaking out of that guy. And you can see some red blood cells that would be in there. That's all they're trying to show us in that top left picture there. But you just can't tell because there's no color. See what it says there? It says, 1, injury to the lining of a vessel. Happens every day. I would hate for you to think that this is some rare event that's the result of a big traumatic accident. It's not. Look, just broke hundreds of blood vessels in that land. Happens every day. So this is an everyday occurrence. We're repairing blood vessels all the time. Now wait, when a blood vessel is broken, maybe you can even see it up here. And actually this projector might be providing adequate resolution, but when you get your eyeballs close to your textbook, you'll be able to see this. On those broken edges over there, they have like little wormy-like beige things sticking out. They're collagen fibers, everybody. When a blood vessel wall breaks, collagen fibers become exposed in that gap. And then, when blood is leaking out through that gap, platelets in the blood stick to those broken collagen fibers. That's what it says up here. Injury to the lining of the vessel exposes collagen fibers and the platelets stick there. Now what we learned in A&P 1, but it was way back in chapter 1, was that every time one of these platelets sticks, it releases chemicals that attract more platelets. More platelets come. More platelets stick to the broken edges of the blood vessel, releasing more chemicals back into the blood that attract even more platelets, and you get this rapid amplification of this response, positive feedback mechanism, that leads to a massive accumulation of platelets called a platelet plug. Look, our handout packet picture is trying to tell us that. Go down to bubble number 2, and it says platelets release. Well, 1, they release some serotonin. That's going to narrow this blood vessel up here. See the squeezing arrows? Trying to show you that this blood vessel would narrow. So we said that about the serotonin already. But look at the second bullet under bubble number 2. See the second bullet says that the platelets are going to release chemicals that attract more platelets to the site? That's how we're going to form this platelet plug. So more platelets come, they bind and release more chemicals, attracting even more platelets. The platelet plug forms. I ask students to think of this platelet plug as being the first of 3 fixes for this broken blood vessel wall. It's going to get fixed 3 times. The first thing is, and it's just in a matter of a few seconds, we form a platelet plug. Profoundly reduces blood loss out of that open gap. Well, if you're following along on the handout packet, and the second circle picture across the top is trying to show you that platelet plug. It says a platelet plug. Okay, now we could go down to bubble number 3. What does it say in bubble number 3? It says thromboplastin is released. Now wait, thromboplastin was not on our list of platelet chemicals. Remember I made you a list? Thromboplastin comes from someplace else. It comes from the broken blood vessel wall cells. These damaged cells here release a substance called thromboplastin. That's bubble number 3. And then that brings us to bubble number 4. In bubble number 4, that thromboplastin from the broken blood vessel wall cells combines with our third platelet chemical called PF3. The third chemical in our story. I'm not sure if that's why it's called platelet factor 3. But platelet factor 3, PF3, which is on the surface of platelets, they always say it sort of coats the surface of platelets. It combines with thromboplastin from the broken blood vessel wall cells. Is everybody at bubble number 4 with me? When you get these 2 different chemicals, one from the surface of the platelets, one from the broken blood vessel wall, when they combine, they're going to form a new molecule on that bubble number 5 called prothrombin activator. Almost every time you see a molecule who has activator in its name, it's almost always an enzyme. It's going to activate something. It's going to cause an important chemical reaction to occur where some other molecule becomes activated. Does everybody know when you draw a chemical reaction like this, like reactants A plus B are going to go through a chemical reaction to give us product C? Do you know you write the name of the enzyme over the reaction arrow like this? That's what they tried to do right there at bubble number 5. Prothrombin activator is an enzyme, and it's going to catalyze a critical chemical reaction. It's going to make it more likely to occur or make it occur faster. What chemical reaction? The conversion of prothrombin to its active form thrombin. Everybody see that horizontal line? That chemical reaction is going to be promoted or catalyzed by prothrombin activator. Prothrombin is just a plasma protein that's circulating around in your plasma. It's always there. Made usually, we say, by the liver, and it's circulating around in your plasma. It's always there. But it's in an inactive state. Once we make the enzyme called prothrombin activator, it's going to convert the prothrombin, which is inactive, into its active form called thrombin. Everybody with me there? We're above the 6 there, the thrombin. Okay, now we've made thrombin, right? Thrombin is also an enzyme. It's going to make another important chemical reaction. So now think about the word thrombin being over that last reaction arrow at the bottom. Thrombin is going to cause the conversion of fibrinogen into fibrin. Everybody see the last bottom line in the story there? We know fibrinogen already. Look, if you keep your handout packet like I've got mine wrapped around and you flip over the page, were you ready to tell me about fibrinogen on your quiz today? I know it didn't come up, but maybe you were going to say, here's a content of the plasma that I know of, fibrinogen, an important clotting protein. Remember it there? Here's where the fibrinogen comes in. Whenever you see OGEM at the end of a word, that means it's inactive. And usually the molecule has to be cleaved. You have to chop a chunk off the molecule to make it bind where it's supposed to bind and actually work. So the molecule gets shorter and the name of the molecule gets shorter. Fibrinogen becomes activated into its active form fibrin. But you need an enzyme to do it. What's the enzyme that converts fibrinogen to its active form fibrin? The enzyme is called thrombin. How do we get that thrombin? Oh, we have to activate prothrombin, and then we call it thrombin. How do you activate prothrombin? You need an enzyme to do that. It's called prothrombin activator. Where the heck are we getting it? See, we're working our way back up. Where do you get that prothrombin activator from? From the combining of PF3 on the surface of the platelets with the thromboplastin from the broken blood vessel wall cells. See, this is about the point where I have to remind students. Remember, this is saving us from 3 nasty pictures in the textbook. See, they sometimes call this an enzyme cascade, where we work really hard to make one enzyme that just allows another chemical reaction to take place, where that chemical reaction yields an enzyme. And then that chemical reaction gives us an enzyme that allows another chemical reaction to happen that gives us an enzyme. This is an enzyme cascade. They sometimes call this the clotting cascade. Well, this is a really simplified version of it, but adequate, I think, for our needs. Look, fibrinogen was a plasma protein, everybody. See how it says in parentheses it's soluble? We know you could hold up a test tube of plasma to the light and you could see through it. You can't see the fibrinogen. It's dissolved in the plasma. It's invisible, right? But as soon as you touch it with some thrombin, it becomes visible. It begins to precipitate out of solution and it begins to crystallize, literally crystallize, into long threads that you can see and touch and feel. I'm going to dim the lights for dramatic effect. Look, this is very dramatic. Let me get rid of this. Bam! There it is. I was thinking about blowing this one up and putting it on the wall in the living room. Look at this. See this net, everybody? Imagine that about 30 seconds ago that net did not exist. That net is made out of fibers of a protein called fibrin, which a moment ago was dissolved in the plasma. But once we activate thrombin and we've got the enzyme that can convert fibrinogen into fibrin, the fibrin just starts to crystallize and forms these long threads, and the threads all cross-hatch like this to form a net that bridges the gap in the broken blood vessel and it cinches that gap closed. It traps red blood cells. It's like a scab. And this is happening where the platelet plug was. So the platelets are in there too, although you just don't see them. They're not real obvious on the picture, but there are platelets and red blood cells trapped in this net of fibrin proteins. This is a picture of a blood clot. This is a spectacular picture of an actual blood clot, which, by the way, is more technically called a thrombus. So, we're using the word thrombin. It's not bad. Let me see. I'm trying to say this word. There you go, now you just have to turn your head. Thrombus, everybody, there's a blood clot. Is that a great picture? Imagine that it just it's like magic. It just miraculously starts to form this net. Red blood cells get trapped in there, the platelets are already there. And you get a big scab on the side of the blood vessel. This blood clot, or thrombus, I always tell students, is now the second fix of 3 fixes for the blood vessel wall. Okay, if you're following me here, we made it to forming our fibrin. If you follow the arrow all the way back up, I had to kind of darken the arrow in before I photocopied it for you. That brings us all the way to that third picture across the top that says fibrin clot with trapped red blood cells. There's the picture of the fibrin clot with the trapped red blood cells. But here it is too. Here it is again. There's the fibrin clot. The fibrin forms a mesh that traps the red blood cells and the platelets forming the clot, the thrombus. That's pretty good. This happens fast too, everybody. I mean, 30 seconds, usually we say within a minute. So the platelet plug is the first fix in just a few seconds. The clot forms within, let's say, a minute. And that's 2 of the 3 fixes. It's the end of the story on the handout packet, but I want you to think of there being a third fix for the blood vessel wall, and it's probably something you would intuitively think happens. Think about this. Ultimately, the way that we're going to fix that blood vessel wall is that the remaining blood vessel wall cells have to divide by mitosis to replace those lost cells in the middle. Those cells that are gone from the blood vessel wall have to be replaced. Eventually, we have to rebuild that wall, right? I always tell students that's the third fix. You won't find it described in the story anywhere, but eventually we're going to have to rebuild the wall. That takes days or weeks, depending on the size of that gap, for that mitosis to replace those cells. Okay, I want to take the story even a little further. We've gotten to the third fix. Yes, you have to actually repair the wall. But then once the wall is fixed, repaired, and we've got new cells there, you're going to have to very, very carefully, cautiously dismantle this clot, because you wouldn't want a piece of this clot breaking off and then shooting through your bloodstream. Think about that net of fibrin, and if it had just 2 or 3 red blood cells in it, trapped together, that's not going to fit down your tiniest capillaries. It's going to choke out those capillaries and cause a traffic jam. It's going to suffocate and starve downstream tissues. Everybody see what I mean? Now imagine if there was 200 or 300 of those red blood cells trapped in there, when I showed you that some of our capillaries only have 1. So you got a big artery, and this chunk of 200 red blood cells is moving down that big artery, no problem. The artery branches to smaller arteries, and now that big chunk of 200 red blood cells goes down those smaller arteries, right? And now the smaller artery is going to branch to even smaller ones, and that big chunk of 200 red blood cells gets trapped right at the mouth of one of those arteries, and everything downstream suffocates, starves, dies. This is what it is to have a blood clot. I know you all have only ever heard bad things about a blood clot, because all you ever hear about is when a blood clot accidentally breaks off of the wall of the blood vessel and goes shooting through somebody's bloodstream. And then it gets stuck in blood vessels in the brain, or in the lungs, or in the wall of the heart. It could get stuck anywhere, and then kill tissues downstream. But blood clots are not bad. They're happening right now in your body. Everybody, you always hear this. Oh, he's in the hospital, he's got a blood clot. What are you talking about? I got probably 24 blood clots right now. You might have many more yourself. I don't know. If you went skiing last weekend, you probably have 700 blood clots in your body right now. But they're normal. It's part of the normal process of repairing your blood vessel. They normally don't break off and go shooting through your bloodstream. That's when you hear about somebody being like hospitalized because they have a blood clot problem. So after the blood vessel wall is fixed, I want you to know we have to dismantle that clot. The dismantling of that clot, we don't have to talk about the details of it, but enzymes have to redissolve the fibrin back into fibrinogen, so it becomes dissolved, the clot does, but also macrophages help to eat up the clot. The breaking up of the clot is called fibrinolysis, and I think just this word is valuable enough to get out there to you, because whenever you see lysis, that always means to break something apart. Usually we're talking about like a cell that's bursting or something. To lysis, to break apart. So the clot must be lysed, must be broken down carefully so that chunks don't go shooting through your bloodstream. Enzymes and macrophages. But that would only be long after the clot. That's not really like part of the blood clotting process. It's just how we're going to clean up after it's all done. Now we've definitely spent way too long on this. End our conversation about hemostasis, blood clotting. And now, what did I do? And now the last topic, 20 minutes? Okay. The last topic in chapter 17 of blood is blood typing. Almost every time I get to this blood typing topic, every student in the class has already had this conversation in their lab, except this semester I'm having students go, no, we didn't discuss blood typing in lab. We'll see as we progress. We'll see if you guys are also in that category. You know, in our species, we use two different types of blood typing methods, right? We use the ABO blood typing system. That's the one shown up here on table 17.4. That's where somebody's blood type is A, or B, or both, AB, or neither. And if you're neither, we say you're type O. But really, you're just not any blood type. It's like no. You don't want to tell somebody you're nothing. So they gave you a name. You're type O, right? But it means that you're neither A nor B. In the ABO blood typing system, we have 4 blood types: A, B, both, and neither. A, B, and type O. We use this one blood typing system, and hopefully somebody told you in lab, we also use the RH blood typing system, where somebody is either plus or minus. You kind of already knew it, even if it wasn't presented in your lab, because we always say that somebody is like B negative or O positive, right? We put the RH positive or negative thing after the ABO blood type, and we put the two of them together to arrive at the human being blood type. So you know this. But look at the ABO blood typing system. Even if you had a conversation in the lab, I'm hoping to present it to you in this way and have you think of it in this way. In order to understand how blood typing works, I tell students there are 3 rules you should know. The first rule is this. On the surface of your red blood cells, there are identification markers called antigens. I think we may have defined that term 2 weeks ago. Antigen is an ID marker on the surface of cells. Some people are genetically programmed to make a B antigen on the surface of their red blood cells. Our book is just showing those as green circles. It's just arbitrarily chosen a green circle to say, look, there are B antigens on some people's red blood cells. If you've got B antigens on the surface of your red blood cells, that's your blood type, B. Some people separately are programmed to make A antigens and express those on the surface of their red blood cells. Our book has arbitrarily chosen to make these gray spiky looking things A antigens. If you make A antigens, which your genetics tell you to make, then your blood type is A. But some people make both A and B, so they're both blood types. Some people make neither the A nor the B, so they're neither blood type, and we say you're type O. The first rule of understanding the ABO blood typing system is your blood type is whatever antigen, be sure not to say antibody, don't start that ANTI, whatever antigen is present on the surface of your red blood cell. All of your red blood cells would have them. Whatever antigens are present on the surface of your red blood cells, that's your blood type. If you got them both, you're both. If you got B, you're B. If you got A, you're A. Nothing to the first rule. There are antigens that we all make or don't make. There are other antigens on the surface of red blood cells. They're just not involved in this blood typing conversation. There's dozens or hundreds of other surface molecules used for ID purposes in different stories that would also be here. These wouldn't be the only antigens on here, but just these ones are involved in how we determine a person's blood type. Okay, the second rule then is this. Whatever antigen you don't make, whatever antigen you don't have on the surface of your red blood cells, to you that's a foreign antigen. So you're going to make antibodies that would attack and destroy that foreign antigen if you ever saw it. Look, antibodies, we learned already, are plasma proteins. So they're shown outside the red blood cell, out here where the plasma would be. Circulating your plasma, these are antibody proteins. And if you've got a B-type blood person with B blood, they're going to make antibodies against A antigens. The most concise way to say this rule is you're going to automatically make antibodies against any antigen you don't have on the surface of your red blood cell. If you're type B, you make anti-A antibodies. If you're type A, you make anti-B antibodies, and they'd be circulating around in your plasma outside of your red blood cells. If you make both A and B antigens, you wouldn't want to make antibodies against either one of those, because the antibodies would attack and destroy your own red blood cells. See how no antibodies are depicted out here? Now wait, you've got hundreds, thousands of other antibodies for other things. They're just not part of this conversation. Nobody think there's no antibodies in this person's blood. There's just no A or B antibodies in this person's blood. They wouldn't make anti-A or anti-B because those antibodies would then attack and destroy their own blood cells. That wouldn't work. So we find neither anti-A nor anti-B antibodies in the plasma of somebody who's type AB. But if you're type O, then to you, A antigens that look like spikes, those are foreign to you. And B antigens that look like green circles, those would be foreign to you as well. So you're going to make antibodies against both of those. The most concise way to say the second rule is this. Your body automatically makes antibodies. Be out there in the plasma. Your body automatically makes antibodies against any antigen that is not present on the surface of your own red blood cell. That antigen is a foreign one to you. It's hard to put it to words, actually. The picture really does a better job. Morgan, go ahead.
Could you repeat that third rule?
Yeah, I've only given you two so far. There's a third one. We haven't gotten to it yet.
Oh, I thought what you just said was the third.
Oh, I keep trying to say the same thing different ways.
Okay.
Watch. The first rule is your blood type is whatever antigens are on the surface of your red blood cell. The second rule is that you'll automatically have antibodies against whatever antigen you don't make. And it's automatic. The making of these antibodies is automatic, so you're always going to have them. The third rule, then, has to do with donation of blood and who can give blood to who. Actually, go ahead.
O, you give to A.
What's that?
O.
Oh, we're going to get to who can give blood to who. When you try to consider who can we harvest blood from, what recipient can we take blood from, and then donate that blood into another human being, when you consider that, you have to be worried that if we put the wrong blood into this person's bloodstream, their antibodies could attack and destroy those red blood cells, causing clumping of the red blood cells or agglutination. Did you use this word in lab? Agglutination? That's what antibodies do. They clump things together. oh boy, a lot of people just took to the pen. And that makes me think, no, nobody said agglutination in lab. Agglutination is the clumping of antigens. So if we put the wrong donated blood into this recipient's bloodstream, their antibodies could attack and clump those donated red blood cells. And I've been trying to convince you all night that clumping of red blood cells is a problem, because that could clog little tiny blood vessels and lead to the death of downstream tissues by suffocation and starvation. Everybody good with that? Clumping, no good. Big, severe immune reaction to foreign blood being in here. So you have to be very careful, right? So my question to you is this: could I take A blood and donate it, take it out of one donor and put it into a recipient that has AB blood? Could I do that?
Yes.
Yeah, everybody seems to know that you can do that, but here's the reason, here's the test you have to think your way through. Are you ready? Does the recipient, this is the recipient, does the recipient have any antibodies that are going to attack the donated blood? That's the question. And I state the rule like this: only consider, you must only consider the recipient's antibodies when trying to determine this. Does the recipient possess any antibodies out here that would attack and destroy these red blood cells if they showed up here? No, they don't have any resident antibodies here for attacking that donor, so that would be okay to do. You can take A blood and put it into, donate it to an AB person, you can. But if you didn't understand the third rule, which is that you only consider the recipient's antibodies, if you didn't know the third rule, you would think this: wait a minute, I can't take this whole picture, antibodies and all, and put it here, because these green anti-B antibodies then would attack and destroy the recipient's own red blood cells by attacking those B antigens. Do you see that? You must ignore, here's another way to say the third rule, you must ignore the donor's antibodies. You must ignore them. You have to consider only the recipient's antibodies in determining whether there's going to be an immune reaction here that causes clumping. If you try to consider the donor's antibodies, you're going to come up with the wrong answer to every question that says, can this blood type donate to this blood type? You'll always come up with the wrong answer if you're going to take into consideration the donor's antibodies. Ignore the donor's antibodies, consider only the recipient's antibodies. Here's why. When we harvest blood from this donor and we pull their blood through a syringe to pull it out of their veins, that damages a lot of those antibodies. And then those antibodies, their three-dimensional structure changes, now they don't bind to things they're supposed to be able to bind to. Some of them get killed in that process, the antibodies. I shouldn't say killed, because they're not living things. They're just molecules, they're just proteins. But they would fall apart, then they're not going to work. Okay, then we're going to take them, after we pull them out of someone's bloodstream and we've damaged a lot of the antibodies, we're going to now take that blood and freeze it in the freezer at no keystone. The freezing process destroys more of the antibodies. Then 2 weeks later, we're going to thaw that blood out. The thawing destroys more